Hello everyone, I'm Norman Wahlberger. Thanks for joining me on this adventure. We're learning about extending number theory to the Maxel situation. So I'm proposing that this is a huge and beautiful new arena for amateur mathematicians to get involved with, connecting with concrete, beautiful, and I think important new mathematics. And I want to illustrate the general idea by looking at a very specific and important example, the Chebyshev polynomials of the first kind. I'm going to show you how to move from looking at these things from a one-dimensional point of view to a two-dimensional point of view, where we bring in matrix theory, linear algebra, and some surprises are in store for us. So let me remind you that the Chebyshev polynomials of the first kind, defined recursively, say t0 of x equals 1, t1 of x equals x, and then tn of x equals 2 times x times tn minus 1 of x minus tn minus 2 of x. And here's some graphs of them. They're particularly sort of interesting in this box from x equals minus 1 to plus 1 and y equals minus 1 to plus 1. Now here is actually an explicit formula for the Chebyshev polynomials. You can see that you can expand it out in a polynomial in x, powers of x, depending on n. So n is the index, which is a natural number, and k is going from 0 up to n over 2, or the floor of n over 2. So that's the greatest integer less than n over 2 in case n over 2 is a fraction. And the coefficients involved here are, well, these binomial coefficients, n minus k, choose k, and we're dividing by n minus k. So it's sort of a sub-binomial coefficient, you might say, and there's also a sign. Okay, and explicitly, well, one way of getting at it is through the generating function, and the generating function is given here. It's 1 minus tx over 1 minus 2tx plus t squared, involving a dummy variable t. And then if you sort of do the long division, or get your computer to do the long division, you get this expansion in powers of t, and the various coefficients are polynomials of x, which are exactly the Chebyshev polynomials, or polynumbers. And if we list them, then we get this list right here. Okay, so 1x, 2x squared minus 1, 4x cubed minus 3x, etc. These are these various coefficients of the powers of t that you get by expanding the generating function. So today we want to move to something new, okay? And it's this step here, from going from this family of essentially one-dimensional objects, namely these polynomials or polynumbers, to a two-dimensional family. So this is what I'm sort of advocating is an interesting thing to think about, interesting sort of door to go through, okay? So let's have a look. How do we do this? Well, we think of each one of these polynomials as, in this case, say a horizontal string of coefficients, starting with the lowest degree ones first. So this 2x squared minus 1 is represented here in this row with a minus 1 and then a 2. And there's a gap. We're kind of going every second one. That's because the powers here are x to the 0 and then x squared. We're missing an x to the 1 in this one here. And then the next one is minus 3x plus 4x cubed. There it is. There's that row. Minus 3x plus 4x cubed, and so on. So we're just listing them row by row. And now we get this two-dimensional triangular. I haven't spelled that right. There, we get a triangular on Maxel. So a Maxel is a more data theoretic sort of approach to matrices. It's not really necessary that you're completely familiar with that. Just think in terms of a matrix that kind of goes on, so we can extend this by going to the right and down. Okay, and so rather arbitrarily just going up to, in this case, degree 10 or degree 9 or whatever. Okay, but you should think of this kind of picture as just a snapshot of the top left corner of this object, which in principle keeps going down. And we don't have to make any grandiose claims about, what happens at infinity or something. It just keeps on going, and ultimately, realistically, it'll overwhelm our ability to represent it. That's actually what really happens. Okay, so what we're interested in doing now is asking the question, is there any benefit to be gained by going from sort of this one-dimensional point of view, having a lot of one-dimensional objects, to having this single two-dimensional object? Well, the answer to this sort of depends on whether we can apply matrix theory or linear algebra to this resulting maxillar matrix. And More specifically, that involves asking the question whether matrix multiplication, or maybe even matrix inversion, that's the crucial thing, actually has something to say about this. But the first step would be just to look at this thing as a two-dimensional array and see if we can sort of notice anything about it that's maybe not so apparent from this kind of description where we just see the polynomials one at a time. Okay, so have a look at this. Can you see anything about it that's interesting? Well, one obvious thing to do, which is sort of a first thing that you might think to do, is just to factor the elements here and see what kind of numbers are going on here. Okay, this is a kind of a number theory, so factoring is great. So this will factor all of the entries sort of simultaneously into their prime decompositions. And if you sort of stare at this, okay, you see there's lots of 2s, there's some 3s, there's some 5s, and I guess about 7 is about the greatest that you get. So this is strongly suggesting that the formula for these entries has something to do with factorials. Okay, the factorials are growing. The fact that we're not getting any higher prime factors here is a strong indication. So even if you didn't know that there was a formula in terms of essentially a binomial coefficient, you could be steered strongly to that, by just staring at this factorization. So that's a very first important advantage in looking at things this way, is that you can sort of quickly see whether there's likely to be a nice factorial type formula for the entries of the array. In fact, we do know that there's that formula. It's the formula I already showed you before. Well, here's something else that you might notice. You might notice that, okay, like this column here, all the things are even. Here they're all odd. Here they're all even. And then here they're all multiples of 4. These ones are all multiples of 8. And this column here has all multiples of 16. You can check these are multiples of 32, and this is actually a multiple of 64. So suggesting that these columns are sort of multiples of powers of 2. Also, the powers of 2 are kind of obviously sort of strung along down the diagonal, so that's another indication that might be quite something natural. So one way of getting at that is to introduce this matrix here. Okay, let me move it up so you can see. So let's introduce this matrix. Maybe I'll put it over here. So let's give this thing first of all a name. So the Chebyshev Maxel, let's call it, on Maxel is C. And now let's just introduce this diagonal matrix with powers of 2. Okay, 2 to the 0 to the 1. There's also a 1 up here that's maybe more questionable, but okay, we'll stick a 1 in there to make it invertible. And then what we're going to do is we're going to sort of factor out these powers of 2 that are in the columns here. And the way we do that is we compute C times D inverse. So if you compute D inverse, this is a diagonal matrix, so the inverse will just consist of these same diagonal entries, but all of them inverted along the diagonal. Okay, so when you multiply C by D inverse, what's going to happen is you're going to be dividing each one of these columns by the corresponding power of 2. Okay, so you're going to simplify. You're taking out those powers of 2. And you can see that the result is, in fact, simpler. Okay, so this is now a simpler object. And we've got it via matrix multiplication. Admittedly, not a very complicated one because we've just been multiplying by a diagonal matrix. But anyway, we have in some sense sort of simplified our understanding of these Chebyshev polynomials by doing this, right? This is a simpler kind of data structure than the original C up here was. Okay, so let's have a look at this thing here. Can we say anything about this thing now? Well, you see there's 1, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8. Okay, you might think maybe that should be a 2. Okay, but anything else that we can obviously see about this? Not entirely clear. All right, so what's the next thing to do? Well, let's call this the scaled Chebyshev Maxel, okay? C times D inverse. Let's take its inverse. All right, so the inverse of C D inverse, this thing that we've just computed, is D times C inverse. Okay. Now I'm strongly using the fact that we're in a matrix environment here. And this is what I want to do, because I want to check whether there's some linear algebra aspect to this situation. And computing an inverse of a matrix is like a sort of an obvious thing that you should do. If you have a matrix in front of you and you're kind of interested in it, calculate its determinant first, and then, if that's non-zero, calculate the corresponding inverse. That's telling you something important about the matrix. So what's the inverse of this matrix here? Here it is right here. Notice that the minus ones have disappeared. Okay. And what else has happened? Well, it looks a little bit different from this one. It still has this sort of alternating checkerboard aspect. And if you just stared at this for a little while, you might notice that the rows appear to be like Pascal rows, right? 1, 4, 3. Okay. 1, 5, 10. That's sort of like 1, 5, 10, 10, 5, 1. 1, 6, 15, 20, 15, 6, 1. That's the sixth row of the Pascal matrix. Except for, there should be a 20 here, okay? That's the start of the seventh one. The eighth one, 1, 8, 28, 56, 35. The next one really ought to be 70. So this is kind of cool. It's making us think that this is almost like kind of a Pascal matrix, sort of staggered, except that to get that, we would have to multiply this first column by 2. What about this top entry here? Well, that's just sort of there by itself. Maybe we could leave it where it is. So if we double the entries of the first column, except for the top entry, I've just done that, right? So I've doubled all the entries of this first column. So if this is n, then this new thing is, let's say, m. And now I can observe that, this is just a Pascal matrix exhibited in a different fashion. How can I show you that? Here it is here, perhaps. Okay, compare this M here with this matrix here. So have a look at this matrix here. What is this matrix here? Well, it's a kind of a two-sided matrix. It doesn't just go off to the right. It also goes off to the left, okay? So you should think about this as sort of being the center here. Okay, and there's a 1, and then there's a 1, 1, and a 1, 2, 1, a 1, 3, 3, 1. So you see this is just a Pascal triangle, but sort of put symmetrically now so that the central binomial coefficients are right down the middle. That's actually an interesting sort of symmetry. Now that the thing is completely symmetrical, right, along this sort of middle vertical axis. Okay, so how does this thing compare with this? Well, it's just a truncation, right? It's what you get if you just look at that part of it. Okay, let me just copy that and put it over here. So I just copied that half of it, or a little bit more than the half, because I've also included the central line. And this is the same thing as that thing. Okay, this is, I think, quite cool. So it's telling us that if we, let's go back a little bit, okay? So we started with the Chebyshev Maxel, where we just making a matrix or a Maxel out of the Chebyshev polynomials. Now we have a two-dimensional thing. Then what we do is we sort of scale it to take out the obvious powers of 2 that are sort of complicating it, okay? So we take out those obvious powers of 2 and we get this matrix CD inverse, which is just a scaled version of what we started with. And this thing here, it's inverse. So now here's where we're using the crucial property of the inverse of a matrix. The inverse of this thing is the n, okay? And then if we perform this somewhat curious modification to n by doubling the entries of this first column, except for the top entry, okay? Then this new matrix M that we get is immediately just a truncation or part of a staggered Pascal matrix. So from this point of view, if you started with the Pascal matrix, admittedly in this sort of unusual sort of symmetrical form, then you could think about the Chebyshev Maxel as just something that you obtain from it by taking the right-hand side and doing a little bit of a modification to that first column and then taking an inverse and then doing another scaling, okay, admittedly. But the essential sort of linear algebra component is really contained already in this Pascal matrix. So that means that there's an intimate connection with between the Chebyshev polynomials and the binomial coefficients, which of course you can see from just the formula for the Chebyshev polynomials. But this is a different aspect of it, where we're utilizing the inverse structure of the maxels. We're using the linear algebra of this two-dimensional situation to get at this inverse structure, and arguably the inverse structure is simpler, right? It's easier to remember. It's just this Pascal matrix. So we might say, well, what happens if we go back? So if this thing here is M, okay, and it's obtained from the staggered Pascal matrix, and if we write this as D times C1 inverse, so we sort of modify the original Chebyshev polynomial Maxel from C to C1, then we would get that C1 would have to be M inverse D, which turns out to be this thing. So from some point of view, sort of from this linear algebra or Pascal point of view, this maybe is a more natural kind of Chebyshev Maxel. From that point of view, maybe the thing that we started with is not exactly the best thing, right? This might be actually more interesting, at least from some point of view, at least from this point of view. So let's investigate this one a little bit more. So we can compare it with the original Chebyshev matrix. So let's let me just do it. So here was the original one, okay, and the C. And here is the comparative if we're looking at sort of the polynumbers. So the way to get the polynumbers very quickly from the Maxel is just to multiply by this column vector of powers of x. That's basically just churning out the various polynumbers corresponding to each row here. Okay, so if we do that, multiply by this vector of x's, then we get the original list of Chebyshev polynumbers. And if we factor them, we can do that all at once. Okay, you've seen me do this before. So we factor them, we get the factorization of the Chebyshev polynomials, which we've noted before is interesting, but it's not quite as interesting, or not at all as interesting as the expansion or the factorization of the spread polynomials, which we will have to get to in a subsequent lecture. But let us now compare this with this modified thing, this C1. Okay, so this was the original C. Let me put that there. C. Okay, that's the original one. And now this modified one. So there's C1. Okay, C sub 1. Whoop, C sub 1. Yeah, and I'm sort of multiplying it by x. Let me just do something like that. So C1 times this vector x. So there's what you get. And here then the sort of modified Chebyshev polynumbers. And how do they compare with these ones? Well, they're almost the same, right? Because the only thing that we've really done differently is we've modified the first column here. So we've taken the first entries, which are just the constant terms which are appearing in every second polynumber, right? The ones that do have constant terms. Instead of having minus 1 plus 1 minus 1 plus 1, we're changing them into minus 2 plus 2 minus 2 plus 2. That's all the difference. We're not notably changing the other ones. So these ones that don't have a constant term, they're not being changed. Okay, that's curious. And now let me factor this thing here. So let's compare this with, to get them side by side. So here are the factorizations of the Chebyshev polynomials themselves. Here are the factorizations of the Chebyshev polynomials. So on the right, the original Chebyshev polynumbers. On the left, these modified Chebyshev polynumbers, where we've just doubled the constant term where we were able to, except for the top entry. What's the difference? Well, of course, every second one is unchanged because they're not being changed. But the ones that that we are changing, it appears, at least from this relatively limited examination, that we're getting increased factorization. We're getting increased factorization. For example, like let's say, so here this this fourth Chebyshev polynomial. Okay, 1 minus 8x squared plus 8x to the fourth, that doesn't factor. But if you replace the 1 with a 2, like up here, then you do get a factorization. It's 2 times 2x squared minus 1 all squared. And similarly, this one here, we did have a factorization for it, but now we get a richer factorization just by adding or by doubling the constant term. And similarly here, this one here didn't factor at all. But over here, we get a factorization. Does this continue? I don't know. I don't know if it continues. I mean, I'm willing to bet that it does, but I don't know. I don't have a proof. What's the significance of these sort of modified Chebyshev polynomials? Well, I don't know. So the only thing I've sort of done is sort of graphed some of them, like some of these first ones. And I get graphs that look like this. There's quite a few of them here, but you see that they're still bouncing around in a pleasant way, but not quite as nicely constrained in the -1 to 1, -1 to 1 box as the Chebyshev polynomials were. So what can we conclude? So we can conclude that going to this two-dimensional Maxel point of view seems to be a rich thing. For one thing, it allows us to see that the Chebyshev Maxel, its inverse, is intimately connected with the Pascal triangle, arranged in a kind of a symmetrical matrix form, sort of a staggered Pascal matrix. So that is definitely a linear algebra aspect of what's going on. And moreover, it suggests sort of these modified Chebyshev polynomials, which very well may be interesting, maybe more interesting from a number theoretic or factorizable sort of point of view. Okay, so there's, I think, a great potential for study here to try to understand, what's going on with these things. Have these things been studied before? I don't know. Can you say anything about whether these nice factorizations continue or not? These are all interesting questions.